Alright, I can pause this. Okay, nice. So, welcome back, folks. Hello, hello. Good evening. We're going to return to what we were working on. It's been another few hours. Yeah, so the deal is quines. They asked for an example of a quine. So we're going to try to write ourselves a quine. The way it works, so we went through. So it's not such a simple answer. It's relatively simple, but not that simple. What it comes down to is we'll define a function quine, and we'll say it doesn't take any arguments. And what it's going to do is it's going to actually print itself, right? And the way this is achieved is you have the beginning of the function, or you have the function, and what you've got is the beginning, middle, and end. And so the beginning is, well, you're going to use a let to define some variables, right? And there's a beginning, a middle, and an end. So the beginning is sort of just like startup code, you know, like you've got this define, you've got this let, you've got a few different things going on. Let's get the text that we want here. So so that's the beginning. It looks like this part, top part. The middle is going to be some text, so data, we'll call it. And this data will have it's actually going to be an array of information. And we can have a sequence. Let's use a vector. It's going to be a vector. And it will have a whole bunch of strings, a sequence of strings to use, right? Which will consist first of the beginning, which is define quine, right? In fact, we can break this up into two pieces, really. It would look like this: the beginning, the middle, and the end. And we can really just make it two pieces. So at the beginning, define quine, and let, we'll call it data, and so you've got the beginning, middle, and end. The middle consists of the data, which is actually the beginning and the end, in two pieces. And you'll see how this works. So the ending piece actually accesses the data and prints different pieces. So it'll print this. You've got this data, which then has another piece to it. We're gonna consider, because Clojure you can write everything on one line. We're going to consider these things to be sort of just one line, right? So you've got this data, and then inside the data is, we're not going to put the middle piece in there. The middle piece will be left out, which is kind of interesting, right? That middle piece is left out. And then we've got the rest of the commands here. The rest of the commands, which will be this part. So okay, the rest of the commands will be first print. It's going to be string of a few pieces. We're going to concatenate 3 pieces, which is the first of the data, first element, then, right, so first part will contain this piece, first part. Then we want the data to be printed again, right? This whole piece inside, the whole thing, second time, right? Because you're gonna have the first part is this data, and then the data itself with quotes in it contained, and you're going to want to have you have the quote character here we can put in there. Hopefully string we can appropriately can place that, right? So this data is going to be quoted, and then we've got the last of the data, or the second of data, we're going to print, right? So this data is quoted in between the whole thing as a vector, right? It'll print pretty much as it is. And so what you end up with is everything following this piece, the midpoint, looks like this stuff. All of this is going to be copied into this string. And we can obviously remove the now I'm wondering what the quote of this is going to look like. We can compare and do a diff to see, because I'm not sure how many, like what do they call that? I'm not sure which I'm not sure which, excuse me, how do you express that? I'm not sure which. When you quote the form, like what the result's going to look like. You know, how much of this will be sort of persistent, I guess. Which white space is preserved, I guess is the way to express it. So when you place this data in between, right, you have this first part printed, and then so you don't need this, I think. I think this is okay. You don't need that. And then you're going to have, right, this, and this stuff comes after it, and then finally the ending piece. All right, so if we call this Quine and print it, curious to see what we get. So there's let data, now this part, first data, let data of this thing. Here's the part that's kind of funky. We don't need the quotes in there, do we? We don't. We can convert this to a string, I think. Let's see what happens. Now this part is kind of tricky because you don't want to close that there. You want this to have, right, you get another one there, and then you get this piece, which has 1, 2, 3, actually it has 4 here. All right, let's do this. Right, if we do this, and we say, let's take a string of quote of this, and just call it, right? If we do that, we want to get the same two functions, same things. I wonder what we get. All right, let's see if we get ourselves a quine. Hey, really close. Not quite the same though. We don't want define anymore, we want just function. Where do they differ? One of these says let data. So this top one, when you quote it, it's let data moves in a bit. So all of this should be moved in then. And let's see, we gotta go. There's a few, like I said, there's a few. The white space when you quote, it's not obvious which white space is moved. And it's not data in here quoted, it's string data. Let's see how this goes. Wow. Amazing, amazing. So I wrote a quine. I did it. I had to use the internet though, because I wasn't gonna figure that on my own. That wasn't gonna happen. That wasn't gonna happen. Man. Yeah, I mean, I don't know what to think of make of that. That would have taken me forever to figure out. I was getting close though. I realized you did need something that referred, like you needed to know which functions you were gonna call. But it wasn't so, you just needed the data of the strings, right? Yeah. Now, look at this. This apparently would have been a quine also. Are you kidding me? Are you kidding me? Oh, if you took X and concatenated it with X, and take that function and you feed it the quoted string that also gives you a quine. Are you kidding me, man? What? What? Oh, these aren't functions though. Oh no, this is just. Oh, all right, whatever. I mean, whatever. This is not. That's not as interesting. This is. This is a function. I mean, whatever. This is not. And this is a function. This is the quoted symbol. This is a function, this is the quoted symbol, and we're saying call this function with this. Gives you the string of this thing concatenated with this thing. And then if you take the quoting of this, then that's this quoted and convert it to a string. Oh, okay. I mean, I guess, I don't know. This is pretty clever. I didn't think of this. I had to write a legitimate quine. I had to write like a straight up quine. I wouldn't have thought of these solutions. I feel kind of dumb now. Not dumb, but I was getting close to this. I was gonna do something like this. I guess I would have eventually figured it out. Really didn't want to spend that time, man. It's a lot of sitting around thinking about it. This is not a proper function though. That's the thing, actually. This is a function. This is like two-part function here. It's not really a function. They asked for a function. This is a this is a function, man. This is like a quine. Like, give me that quine. This is not really solving. This is kind of cheating, actually, in some sense. A little bit. A little bit. Le quine. Le quine. Yeah, I used to quine. I did it. I did it. I did it. I'm glad to have seen the other solutions. Alright, no more brain teasers, man. No more brain teasers, man. Come on. Enter a value which satisfies the following. Let x and class of x, x. Oh my goodness. Class of x is equal to x and x. So x is something that's becomes true. It's truthy, and the class of x is equal to x. Can we just do int? It's a puzzle. If we do nil, no. What? I want to say like an empty set or something. I don't think so. Data structure. What is, all right, what is equals class of x? Let's just do class of x, right? Let's just open up a line, a REPL, aligning in REPL. Some class of x. It's a long, okay. Like what could we even put in here? Alright, that's just an anonymous function. Nice. Okay, Java line class, class of Java online class. Nice. Come on, man. The class of Java.line class is equal to Java.line class, and Java.line class is truthy. False. Oh. And true. True. Okay. No, it's truthy, but it's not necessarily true. True, it's got to be exactly true. Not false, really, is what you want. Well, no, also would not be. Not false would give you true. See, this is remember I was talking about you know, a binary. Doesn't like this could be a paradox. We were talking about paradoxes earlier. This technically could be a paradox. Appears to be a paradox, right? If you took an object that's in a truthy language, right? You've got true, false, and something it's maybe sometimes true, sometimes false, right? Like Java.lang is not false is true, but if it's true, it's false. Does that make sense? Not false is true, but true is false. It's not true. It's also not false simultaneously. How could that be? Alternatively, how about not false and not true? It's both not true and not false. Oh, how about this one? How about this one? And yeah, that's a contradiction actually. Look at that. How about that? Is it true? Is it false? No. Not exactly true, not exactly false. What does that mean? What does that mean? I'm going to call that Will's paradox. You ready? Oh my goodness, I'm going to be famous. Oh my goodness, I'm going to be famous. Alright, there we go. False paradox. False, true, false, false. Everything's false. So this is the riddle. Figured it out. Heck yeah. Heck yeah. Call that easy. I think I'm incredibly not clever. Let's see other solutions though. Other things that work. Class. I guess these are the only ones that work. Class of string. That's interesting. Oh, I guess. Oh, that's actually pretty clever. If you repeat class multiple times, I like that. Oh, that's cool. Watch this. Class of anything of 1, right? How about that? Ah, look at that. Ah, more generalized solution. That's pretty clever. Class of class. Classy. Getting classy here. So the issue wasn't that it needs to be a class. It needs to have a certain functional kind of a property to it. True class identity. Whoa. Whoa. Oh, because it would evaluate true. And then, wait. True class identity would say class of true class identity would give you true. And then this would give you class of true, which is true. And this gives you true. And this also gives you true. Could you just do true in here? Would that matter if you need true class identity? I don't know. No. Or true identity class? Yeah, true class identity. Oh. Oh. Look at that. Oh, talk about hacking. Oh man, that's funny. Hold on. I'll get back to that in a second. Oh, I didn't think of that. That's hysterical. Because it's a binding, you can throw in, you can bind class to something else. Oh, these hackers. These freaking hackers. They just bound class in this scope to another function. They just give me the identity, and they made X true. So this is true, true, and then identity of true is true. So just true across the board. So it makes everything true. Hack it to make everything true. Oh, that's hysterical. Oh, that's so funny. Oh, wow, amazing. Another interesting solution. Alright, that was good. That's really fun. Wow, alright, nice. The Quine thing was just kind of like, not cruel, but irritating. Because it's like, man, why you gotta do me like that? But this is a little more, this is a little cuter. This is easy enough to figure out, and then also you could come up with some clever approaches. Excuse me. You can abuse the idempotence of class. That's how you would express this. Yeah, class is idempotent. It'll just keep returning the same class over and over. That's actually what the initial solution is too. It's basically if you use class itself for all of these, then it becomes idempotent, and class of class gives you class again. But you could actually class of something random, and that'll give you that class here, and then this will also give it to you there, which is interesting. You can't simply take the class once though. Oh, maybe you can. No, you can't. Oh, can you? No, you can't use it. No, wait. No, I don't think so. You can't just take class once though, because class of 1 will give you a long. So you get long here for x, long, and then class of long will give you long or class of the class. Does it actually? Oh, I don't know. What does this do? Failed unit tests. Really? Oh, you know what? Because I think this gives you the class of the class is just Java class. I think that's why. Yeah, it's the item potence, but in particular, this will give you java.lang.class or just class. This is actually equal to class. I betcha. I betcha. Yeah, okay. So it's idempotent, but it's actually just the same solution again. Okay, interesting. Yeah, so you can hack it, but ultimately it's just there's a certain idempotent property of the class function. Is I guess really what they're looking for here. Very interesting. Search and data juggling. Love triangle. Everyone loves triangles. Not everyone loves love triangles. And it's easy to understand why. They're so wonderfully symmetric. Except scalenes. They're not great. Your passion for triangles has led you to become a miner and part-time Clojure programmer, where you work all day to chip out isosceles-shaped minerals from rocks gathered in a nearby open-pit mine. There are too many rocks coming from the mine to harvest them all, so you have been tasked with writing a program to analyze the mineral patterns of each rock and determine which rocks have the biggest minerals. Someone has already written a computer vision system for the mine. It images each rock as it comes into the processing center and creates a cross-sectional bitmap of mineral 1 and rock 0, concentrations for each one. You must now create a function which accepts a collection of integers. Each integer, when read in base 2, gives the bit representation of the rock. Again, 1s are mineral and 0s are worthless scalene like rock. You must return the cross-sectional area of the largest harvestable mineral from the input rock as follows. The minerals only have smooth faces when sheared vertically or horizontally from the rock's cross-section. The mine is only concerned with harvesting isosceles triangles such that one or two sides can be sheared. If only one face of the mineral is sheared, its opposing vertex must be a point. The smooth face must be of odd length, and its two equal length sides must intersect the shear face at 45 degrees, i.e. those sides must be cut even diagonally. The harvested mineral may not contain any traces of rock. The mineral may lie in any orientation in the plane. Area should be calculated as the sum of ones that comprise the mineral. Minerals must have a minimum of 3 measures of area to be harvested. If no minerals can be harvested from the rock, your function should return nil. What am I even reading? I don't understand. Oh, these are so involved, these questions. I mean, they're good. They're good. Proper challenges, right? But I am like counting down the problems to the end here. I'm so ready to move on. I mean, these are interesting problems, don't get me wrong, but it's just, this feels like it's kind of droning on a bit, all of this stuff. Okay. I did realize that though also is that I mentioned that the concentration of difficult to hard problems is gonna increase as we go, because just the way these things are structured, once you get through the easy problems, then you're stuck with hard problems. So once you get through most of the problems, you've most likely gone through the easy problems already. So it's just gonna be easier or medium at the end, one after another. All right, so let's start with what they wanted to talk about with computer vision. How computers can be made to gain high-level understanding from digital images or videos. Perspective engineering seeks to automate tasks that the human visual system can do. That's pretty cool. I think computer vision is amazing. Awesome thing. Definitely interested in computer vision at some point in the future. I don't know when exactly I'll be that interested. Maybe it's not as interesting as I think. It's cool. Don't get me wrong. It's pretty cool. But I think ultimately I might not need all this stuff. Convolutional neural networks. Kind of want to learn about that because it comes up often enough. Stuff. Anyway, this is all kinds of stuff to learn about. Cool. Leave that for now. So computer vision is the thing. The computer, also known as bitmap, bitset, bitstring, or bitvector, is an array data structure that compactly stores bits. It can be used to implement a simple set data structure. A bit array is effective at exploiting bit-level parallelism in hardware to perform operations quickly. A typical bit array stores k times w bits. W is the number of bits in the unit of storage, such as byte or word, and k is some non-negative integer. If w does not divide the number of bits to be stored, some space is wasted due to internal fragmentation. So they call it internal fragmentation. It's a heck of a word for what that means. It's just some extra unused bits in your hardware, in your hard disk, in your program. Okay, fair enough. Compactly stores bits. Can be used to implement a simple set data structure. Bit array is effective. Okay, bitmap. Alright, bit set, bit string, bit vector, bit array. Okay, I understand. So basically it's just a bunch of ones and zeros in like an integer or a series of integers. So, you know, they give you hexadecimal, so 4-bit numbers you're going to operate on. So create a function which accepts a collection of integers. Each integer, when read in base 2, gives the bit representation of the rock. Again, 1s are mineral and 0s are worthless, scaling like rock. You must return the cross-sectional area of the largest harvestable mineral from the input rock as follows. So a couple things. One, I'm wondering if I should actually write a routine to convert the integers. So that way I have a quote-unquote board, so I have something to work with here. Does Clojure have a bitmap wrapper? Does not. Nice. I can write routines to get from a particular row, a particular index. Maybe I could write a routine. I'll abstract that away. Just a real simple thing that what does it do? Simple routine that does what? I completely forgot what it was I was thinking here. Excuse me, yeah. I can write a routine that gets from the problem is that there's a getIn function that you want to use. Yeah, I guess I'll just abstract that away too for our purposes. Should be fine to thinking about it. All you do to get, by the way, what you're looking for is you bit shift and excuse me, you bit shift one bit to whatever index position you're interested in, and then take a logical AND over that number and the number that you're the bitmap. And that'll tell you, and then if the value is greater than 0, then you've got what you want, got what you're looking for. You know that the bit is there. You could say, is there a logical AND Clojure? Or bitwise? No, I don't want logical. I want bitwise AND. Cool. So it's there. The bit AND. Just getting the values from the bitmap. Considering. Yeah, we don't actually need to convert this to anything then. If we use that, we just abstract that away using a bit AND. All right. Isosceles shaped minerals from rocks gathered in, a nearby open pit mine. Isosceles means they've got two lengths that are the same. Two sides of equal length, yeah. So not equilateral triangles we're looking for. We're looking for isosceles triangles. Okay. There are too many rocks coming from the mine to harvest them all. So you've been tasked with writing a program to analyze mineral patterns of each rock and determine which rocks have the biggest minerals. Alright, so you want the biggest mineral of the rock, the biggest isosceles triangle you can find. Someone already wrote a system for the mine, images each rock as it comes into the processing center, creates a cross-sectional bitmap of mineral and rock, concentrations for each one. You must now create a function which accepts a collection of integers. Each integer, when read in base 2, gives the bit representation of the rock. Again, 1s are mineral and 0s are worthless scaling, like rock. Okay. 0s are not what you want. Must return the cross-sectional area of the largest harvestable mineral from the input rock as follows. Minerals only have smooth faces when sheared vertically or horizontally from the rock's cross-section. So what do you mean by sheared? I think I typically know what that means, but let's make sure. Cut the wool off a sheep or other animal, break off or cause to break off owing to a structural strain. So shear is to break off. Okay. So the minerals only have smooth faces when sheared vertically or horizontally from the rock's cross-section. I don't really know what that means. I don't know what they're getting at here. I don't know if it matters. The mine is only concerned with harvesting isosceles triangles such that one or two sides can be sheared. One or two sides can be sheared. Okay. How does that work? So you can, okay. I still don't know what they mean by one or two sides. Like this one has 3 sides that are being cut out of the rock, it looks like. I don't really get it. I mean, I guess we're just looking for isosceles triangles, ultimately. I don't know. If only one face of the mineral is sheared, its opposing vertex must be a point, i.e. the smooth face must be of odd length, and its 2 equal length sides must intersect the shear face at 45 degrees, i.e. those sides must cut even diagonally. I don't know what that means. Only one face of the mineral is sheared. Its opposing vertex must be a point. Okay. The smooth face must be of odd length. I don't know what they mean by smooth face. There's so many things here I don't understand what they mean. It's really confusing, hard to follow. And its 2 equal length sides must intersect the shear face at 45 degrees, i.e. those sides must cut even diagonally. I don't really know what the meaning of this is. What do they mean? What? I don't get it. Harvested mineral may not contain any traces of rock. Okay, got that. The mineral must lie in any orientation in the plane. Area should be calculated as the sum of ones that comprise the mineral. Should be calculated as the sum of ones that comprise the mineral. Minerals must have a minimum of 3 measures. Minimum of 3 measures of area to be harvested. Must have a minimum of 3 measures of area to be harvested? What does that mean? 3 measures of area? I don't understand that. If no minerals can be harvested from the rock, your function should return nil. Do any of these return nil? This one does. Right, so, oh, I see. There's got to be at least 3 measures of area. Oh, I understand. In other words, it's got to have the area's got to be at least 3. All right, so none of these solutions will be less than 3. Okay. So we're looking for isosceles triangles. So I guess that's the basic gist of it. And they can be in whatever orientation. They've just got to be, 2 sides need to be of equal length. And you could have 2 diagonals. rather than one diagonal. I mean, okay. Let's go sit down, lay down for a bit, ponder this question. This is gonna require some pondering. Exactly how to do this. Definitely don't know that offhand. How we should do this. Okay. I mean, all right. Okay. Let me lay down for a minute here, a few minutes. Oh, let's just ponder. Oh, how can we do this? How can we solve this isosceles triangle question? Excuse me. This question of triangles, the triangulating question. No, 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 Oh, hold on. Here's someone. I think Dad's calling me. I'll be right back. Okay. Sorry about that. Okay, we're back. So I meant to take a break, but not that much for that long of a break, but that's okay. So this is an interesting question. Do I have an answer? Any kind of an answer? No. I don't know. Well, we could start by setting up the scaffolding here, at least. What do they call this? This is triangles, or just mineral triangle. And we're going to have variadic, no, sequence. We'll say ints, or vals, or v's, x's is good. I like using x's. And what we're going to do is get a whole bunch of spaces here and say, go one by one. So, oh, actually, oh, okay. Okay. What was I even doing here? So, I don't really have a good idea for a solution for this. I don't even have ideas. I'm just kind of. You're looking for isosceles triangles, huh? How would you even begin with that? Okay. What am I doing here? Right. Isosceles triangles. What are we doing? How do we do this? What is the issue here? Well, you could try with a brute force solution. It's been a while since I found something that didn't already know the problem. We see it in some form already previously. So yeah, I mean, well, the triangles could be anywhere, right? I mean, you could, brute force solution is just try every possible triangle at every possible position and see if that triangle is quote unquote full. So all of the positions in that supposed triangle exist. All of the positions in that triangle exist. Yeah, meaning they're all contained in the bitmap. You could write an algorithm that performs that check. And then of the triangles that do exist, take the largest one and write all possible isosceles triangles from that point, I suppose. So you could do point by point and then say there's at least, so there's one for each size of isosceles triangle. There's sort of three different, let's see, kind of positions they could be in. 1, 2, and I suppose there's about 3 different ways they could exist. Each point. The point could be, yeah. The point that you're looking at could be one of 3 points of a triangle that fits there. It could be, there's sort of the right angle point or the other 2 points, or the 2 45-degree angle points. Right, in these isosceles triangles, I think they always have a right angle. Yeah, it looks like this has a right angle always, right? Yeah. So yeah, it could be this, could be the right angle, or it could be the other 2 angles, the other 2 points. Could be positioned here. The right angle could be. No, that's not correct. I don't know what I'm talking about. I don't know. I don't know. This point, it could be side like this, or no. I mean, you could have, like, at this point, you could have a triangle this way, a triangle the other way, a triangle this way, this way, this way, this way. Could be this way. I want to say I don't know. This one's kind of difficult for me. I think I would want more test cases for something like this, but basically you could have like a triangle like this at the point that you're interested in. A triangle. There's a few different triangles that could appear here. Could look like this, could look like this. Could look like that. Could be one of these kind of triangles. Could be the other way, the same triangle. Could be this way, the same triangle, right? There's a few different positions you could check. At least 4 like this, and then here there's another 4. Here there's another 4. So these 4 red ones. There's the 4 black ones, and I guess there is only 8 different orientations really. It's like this way, 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 and all the way across. Yeah, I guess there's go 1, 2, 1, 2, 1. No, not that way. 2. And then finally 1 and 2. Yeah, there's really eight different. I don't know really how to show it, but basically you're rotating between these 8 different sort of orientations, I guess. Yeah, I mean, I guess that's not too bad to do a manual check over all the different possibilities. It seems kind of bad though to do it that way. It can be done. It's just you're going to do 8 different orientations, and then you're going to do whatever n is in each direction, so 8 by n, and that's going to be per position, so 8 by n squared, so it's O(n) cubed algorithm to go through, walk through every possible triangle. Not to mention the triangles themselves. No, sorry, it's 8 times n squared. It's actually quartic, not cubic. It's quartic. The amount of checking that you'll need to do, because each triangle in theory is O of n time to check if the whole triangle is all ones. An alternative approach might be to I actually don't know. That seems like the simplest approach, which the running time of that would be probably okay. For the most part would be okay, I think. To improve that running time though, I don't know. Not only do I have to set this up properly, I have to actually do all of that checking correctly and not efficiently, but just correctly, checking all those values, which can be kind of awkward, I think. Probably would want to organize it into like horizontal and vertical checks, and then, you know, or just horizontal checks, maybe. I'm not really sure of like an easy, like generalized way to check each of these triangles, given the endpoints, right? The starting point, the other 2 points. Starting one vertex, so you could find the other 2 vertices that you're interested in, and then that gives you the 3 vertices that you want to use. Even when you have those 3 vertices, determining whether or not all of the ones between them. Actually, no, maybe not. I take that back. That might not be too bad, after all. You could probably write a routine that's simple enough that could check all the pixels in between in that area. Probably would want to use a line by line though. Could do horizontal lines or vertical lines, something like that. the other idea is like maybe there's a way to get the using something like, so this seems to be a computational geometry question ultimately. Computational geometry question, which I TA'd a course in computational geometry, so one would think that I was somewhat good at this, but the truth is I'm okay. I'm not like fantastic, but I know some things. Actually, no, I should say it's been 6 years since I even looked at any computational geometry in any, I don't know, significant way. So maybe not. Maybe I'll just say I'm out of practice. It's a better way to say it, I think. Better way to think about it. What I would like to do, I think, ultimately, is keep singing. You probably want like a convex hull type of thing. No, not really. No, convex hull's not what you want. You want something else. You want... I'd have to kind of ponder this question for a while to really get something that's better than the naive approach. I don't know. Like, I just flat out don't know something better than that. Again, these test cases, it's fine. Like, you'll pass all these test cases using something that's, kind of inefficient. But if you had to do this from, more than this, you would definitely want to think of a better... Oh, no. I forgot. I'm sorry. Alright, looks like we're black screen here. Sweet. Alright, how do we get black screen back? I think if I try to add back one of these display captures. There we go. Worked. Not sure why that works, but it worked. Nice. All the best. So what was I doing? I don't know, man. Maybe that's what I should code up. Just do it. Like I said, I don't have a better solution than the naive solution. Don't have one. Just outright don't have one. If I spent more time on this problem, and I'm talking a lot of time, I could come up with something more efficient, but I don't really want to spend that much time on this. And I think that's the truth. I think that's just the reality of the situation here. I think better not. Probably not. Maybe not worth it. Maybe not. Yeah. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. So do 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 do. No 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 no. Wondering if I should think about this more or not. Let's think about it a little bit more, a little longer. So maybe there's a recursive algorithm we can use, like a what you might call a like a flooding kind of algorithm, like a breadth first search, or a depth first search, breadth first search. Maybe a breadth first search is what we want from each point that, well, there's sort of these connected components, you could argue, and maybe each of those connected components you could check for a triangle. Starting a breadth first search at every... Alright, so I think what I'm going to do is code up the naive algorithm, right, and run that and see how that goes. And do that. And then I did come up, not that come up, but I'm pondering maybe you can perform a kind of searching algorithm where there's an algorithm called, there's this islands algorithm that's called, I've forgotten the name now. Actually, I took the quiz for 2 Sigma a while back. That they asked this question, and the question was or is, what's it called? There's a name for this thing. It's a islands wiki algorithm. I forget what it's called. It's almost explicitly for this. No. No, it's not this one. It's not the island algorithm. It's useful for urban heat island. Interesting. No. It's used for something very specific. Number of islands algorithm. I forgot what it's called. You could use depth first search. That works too, and counting the number of components. But there's one in particular that's important. It's more efficient than that. Union find. That's what I'm looking for. Yeah, that's the one. Disjoint dataset structure. Yeah. This is pretty cool. The union find disjoint set, union find forest. This is a very efficient algorithm. So you could perform union find over the elements. Although I think depth first search is better for the connected components. Maybe just because it's simpler. But bottom line, you can find the number of connected components. Like what you could do with a depth first search is just keep a map of like, I'm actually not sure if the union find is any better than using a simple depth first search for this problem. Thinking about it now, I'm not really sure. Applications, partitioning of a set, connected components, so graph. Key component implementing Isosceles algorithm. Interesting. Anyway, what was I doing? You could use DFS. Yeah, you could use, so what I was thinking is you could use DFS to sort of get each connected component and then operate on each connected component and say, okay, what's the largest triangle that I could fit in this connected component? That may be better. That may be a better approach. Because I think you can do like I guess you could sort of trace the bounding box, something like that. I want to say like you could, once you've got a connected component and it's at least of size 3, you could say like, all right, what triangle can I fit in this box, right? You could ask that question and sort of like keep minimizing. You could start with the largest triangle that doesn't fit and then just keep making it smaller until it fits somewhere. And that might be a more efficient algorithm for this. That's an idea. Yeah, that's an idea. Yeah. I think I just want to code up the naive one because I know that works. The one that's less naive, quote unquote less naive, is, I don't know how I would exactly implement that though. I mean, in theory, you could take, right, this connected component, it's got at least 3 values in it, and then you got to figure out, okay, well, how could I fit, can I fit any, what's the largest triangle? Like start, I guess you'd have to take like, I don't know where you even begin. Excuse me, I guess like the bounding box of that component. And then you'd say, okay, that doesn't fit. So there's about how many different triangles that you could have, about 8 different triangles you could consider from the bounding box. And I don't know, I guess you could just keep trying. I want to say that once you've got this bounding box, you could do kind of a logarithmic search, sort of looking for, I guess, one of the corners of the triangle of interest, maybe. I don't know. I'm not really sure. It's not clear to me at all how you might conceive of an algorithm. It seems like you could do it. You could get the connected component and then perform a logarithmic time check to figure out which triangle with a certain orientation, the largest triangle of any orientation that would fit. Maybe you could fix the orientation of the triangle and then try there's 8 different orientations. So you could try each orientation where it could fit and enlarge that value as well. Like you want to get the largest such triangle that could fit within that bounding box, which actually is just it really just becomes like a sub problem. So actually what this ends up being is the DFS into connected components just performs a recursion over different subsets of the problem, which is just the same problem again, but now, now we know it's just one connected component that we're looking at. It's not really, it doesn't really solve anything doing that, I think about it. But if it's just one connected component, you could say somewhere in there fits a triangle, possibly. If there's at least 3 values, know that there is a triangle. Maybe you can do, but no, that doesn't really work either. How can we do this? How can we do this? How can we do this? Alright, maybe I shouldn't think about this too much more. I think in theory it can be done. I don't know the algorithm offhand though. You kind of want to like narrow down possibility. I mean, that's kind of what you have. The search space is really, you know, there's 8 different orientations, and then, you know, whatever the size of your set is, size of your subgraph is, you know, that sub bounding box, that, you know, that times the number of orientations, and then there's also the potential sizes, which I guess would be sort of the length. So there's a sort of cubic search space that you're working with, which, I guess you could do something logarithmic, hopefully, maybe. Yeah, if you could do something logarithmic there, that'd be great. But it's kind of hard to. It's like basically a binary search is what you're looking for. So you want to say, so binary search on what? There's sort of 3 directions to look at. What you'd want to do ideally is try to figure out a way to order these 2 tuples, create an order on these tuples with respect to all 3 variables, right? And then you can maybe perform a binary search over that order somehow. Or use something like, I think they use, what are these, quad trees, something like that. It's like a quad tree maybe. But there's also an issue of the size of the triangles too. What would you be using? How would you use quad trees though? Yeah, I don't know. I don't really have the solution in any obvious form right now. Definitely not. I'd have to really think about it for a while. I'm curious if other people have better solutions. But that's probably how you can do it. I think you can use a you know, get the connected components, which create subproblems that are connected, and then you can use some kind of binary search. Maybe, hopefully, some kind of binary search. I think I'd have to see a solution to how you do that. I think I'd want to see how someone implements it, but you might be able to do that, a binary search. What we're going to do, though, is not a binary search. We're going to just brute force this one, and that's going to be great. That's going to be great. Okay. It's going to take a while. This is going to take some time. think also I'll extend the time that I was going to spend a bit. Oh, my timer stopped on me. Alright, how long have we been streaming for? Let's just take a look. 2 hours and 18 minutes, and I'd say took a break at some point here. I was just gone. That one concurrent viewer is myself. Amazing. I don't know how long that was gone for. It's probably gone for 20 minutes or so, 30 minutes. I don't know. So we'll just throw another hour in here. It's fine. Yeah, I think we'll try to brute force this. So the brute force will look like the following. Mineral triangle. And what we're going to want to do, we'll be looking to do, is not perform that algorithm that I was hinting at that might exist, but we'll try to perform an algorithm that does work with certainty. And we want a few things. We want, for starters, directions, or directions, which there's 8 different directions we want, but we want more specific than that. We want pairs or orientations, really. Orients. And this is going to be a vector of vectors, 8 vectors in it. And we're going to have a few different directions. Basically, the directions are going to be rotated clockwise. So they're always going to be 90 degrees from each other and clockwise. So you can say something like, can you do, well, there's 8 directions, right? And we want rotate 90 degrees. Yeah, that's kind of what we want. We want something like this. We want directions, of which there are 8, which we said will have, I like this approach, -1, 0, 1. And you're going to say for I of D, J of D, when not equal I, J, and 0. Right, and you're going to take I of J, so those are the directions, and then we're going to say, do better than that, I'll try to. Rotate 90 degrees. Given a row column, or YX, we'll call it, you want to return 90-degree rotation. What does that do? That means you take your XY coordinate, or YX coordinate, whatever it is, XY we'll call it, that vector, and it's going to be, we'll say 90 degrees upwards, means x is some r times cosine theta, right? So this basically is what happens when you rotate 90 degrees. You have something like this. You have some vector on a unit circle, which this is some theta degrees, and you say this is r times cosine theta, sine theta, what is that? It's, if we want to go up 90 degrees, sine, so cosine theta is the x coordinate, sine theta is the y coordinate, right? And now you want to calculate what is, translate this to x cosine theta plus 90 degrees and r sine theta plus 90 degrees, right? You do that, and you can use, there's a rule, which is the double angle formula, which is cosine of a plus b equals sine of a plus b. It's not double angle, it's the summation rule of sine cosine, which I don't recall how it works exactly. Sine sum rule. Yeah, trig without tears. Nice. Something you would just memorize. Oh, this is complex numbers, we don't need that. Sine of a plus b equals sine of a cosine b plus cosine of a sine of b. And then the other one is cosine a cosine b minus sine a sine b. Right. So that gives you b equals 90 degrees. Gives you, okay, so cosine of b is 90 degrees, cosine of 90 degrees is 0. So this is negative, and sine of 90 degrees is 1. So it's a negative sine of a, right? And then this is, so cosine of b is 0, right? So this becomes also cosine of a. So we get here, which means we're looking at negative r sine of theta, r cosine theta, which is exactly, so r cosine of not of a. Isn't really a proof, but this is just sort of a neat way to see this. Alternatively, you could say if you started with xy, you're going to go to swap y and x, or let's see this, yeah, there you go, swap y and x and negate the first one, negative yx. 90 degree rotation. It's basically the way to do it. So you're just going to get negative yx. Let's rotate, and you're going to say orientations are then it's going to be a map of the following functions over directions, which is going to have return these two, which is the first direction, and then rotating the second direction. So you get your orientations that way. And now you say brute force over we can say get value or just get bit. Just abstract this one away so we have some row column. And we're going to go ahead and say, or we could do RC. We're going to say it's going to be x's. So the row will be x's of get, x's 0 by default, and we return the row. And then we want to get true or false here, which consists of, so this gives us a number. We want to bit and this number with, and then we want to say if it's greater than 0 or not. If this is greater than 0. And what we're going to bit and this thing with is we want to bit shift left x and n. Bit shift to the left 1, and we're going to use n is the column. It's actually going to be the other way around. We just assume the okay. We're going to say count of x is minus c. And those bits, okay. Yeah, so I'll give you true or false. What you want is so you're going to bit shift a 1 to the left. Now, if you're in the 0th position, it should actually be all the way to the left. So that's going to be the count of x's. That's how many bit shifts you need to perform. So if there's 4 bits, you bit shift once. Now it's in the second position twice. So actually you need to subtract another 1 here. All right, once, twice, 3 times, 3 bit shifts from position 1 will put you all the way at the 4th index, or 3rd index, however you want to describe it. 4th position from the right. If you want to, if you want the 3rd position, right, then you end up with no bit shifts. Right, it's going to be the count of x's, which is 4 of them, minus 3, minus 1. Yeah. Great. Okay. Fair enough. D directions, rotate, orientations, has bit. Need these different subroutines to build, or building blocks here. that I know we're going to use. I want to iterate over all the orientations, so we can use. We're going to do an iteration that does a few things. We can even make this more, even simplify even further. So we can say has triangle, right? Given we've got your x's, we've got an orientation, given an orientation, and a size, or size, given an orientation and a size, and a starting position, an RC, or row column. Could just destructure it right then and there. So what we're going to do is we're going to extend the orientation out. Extend the, gonna get these, we'll have 3 points to consider for this triangle. And we want to know if all the pixels in between those 3 points are all ones. Now that's an interesting question. Shucks, man. I don't really have a simple algorithm for that either. I want to say you could use kind of a Scanline algorithm, but the problem with this is, like, if you do horizontal lines or vertical lines or what have you, you actually need to trace, like, like if you're just given 3 arbitrary points and you want to figure out, okay, these 3 points, they define between them are 3 different lines, and you want to scan line between the, you know what you can do? You can use what's called a convex hull trick, which is kind of interesting. And you can use that to figure out which line is the lowest line and which line is the highest line. Because you're dealing with a convex shape, you can use the convex hull optimization, the convex hull trick, to find the topmost part of the convex polygon and the bottommost part of the convex polygon, and then find the associated point, right? Using that line segment to calculate the point that you're looking for, and then for both the top and the bottom, and then just check that if everything, the line, vertical line between the bottom point and the top point, if it's, check if that is filled in or not. I think with triangles this is a little bit simpler than using the convex hull trick, but I think the upshot is the convex hull trick kind of abstracts away problems where maybe your bottommost line is not so clear, not so obvious. Could be two line segments that make up the bottommost line. I want to go lay down again because now I'm thinking I'm going to write a convex hull trick convex hull trick implementation, which is probably more involved even than this question is, but we can do it. And then from there we can say, yeah, what we want is a sort of a sub algorithm that says given 3 points, or just given one algorithm is given a convex polygon in 2D space, can we determine if that polygon is completely filled, right? We're given the sort of the line segments that define the bounding edges, sort of the convex hull, which is a more interesting algorithm probably than this one. Well, not more interesting, but an interesting algorithm. Excuse me. Actually, I could probably do it even more efficiently. The convex hull trick really works with when you're dealing with lots and lots of lines, I think, intersecting or otherwise. That's a linear programming thing, linear optimization. Like, you know, we have lots and lots of lines intersecting with each other for the top of the hull and the bottom of the hull. And those aren't just line segments, those are lines that intersect, really is what it works for, not so much line segments. Actually, for the convex hull, you may very well have something I guess is not completely convex. Could happen for the convex hull trick too. No, actually, the convex hull trick does not work in this instance. Get the wrong answer. Yeah, it's always convex. It's always convex if you're looking at the bottom envelope. The problem is if you have two lines like this. No, actually, this doesn't work for the use case I'm looking at. Convex hull trick is going to give you going to give you this bottom part, but you may actually want this guy, right? This actually is not what you're looking for. Never mind, you can't use a convex hull trick. No, I actually cannot do that. The reason is actually I think what you're going to want to do is just figure out at each point, try all three lines. Yeah, because the problem is the convex hull trick, your line segment is defined. You could brute force, I think, for the triangle. Actually, you could brute force what you're looking for. But the problem you'll end up with is this lowest point actually belongs to this line segment. but it's a line segment, not a line, which is a different understanding, which means that you don't even include this line in your calculation for where the lowest point is, which is kind of weird. I don't actually know. If you were given a convex hull, how would you find the lowest x coordinate, the lowest point? You could brute force it over all the different line segments that are defined over that interval. But there really is only 2 line segments that are defined with that value. So I suppose you could actually you could technically split your convex hull into 2 pieces, or your convex polygon. Basically, there must always be a rightmost side to your hull, or to your hold on a second here. There must always be a rightmost and leftmost side to your hull. And so what you can do is say, let's make this red here, make this green here, and then you can say, okay, take these line segments. There's going to be these 2 line segments. Take these 2 line segments or sort them from left to right, on their endpoints. Similarly here, right, on their x coordinates. And then you can say, to give me the topmost, right? We know that these are the top ones. From those points we can tell, because we know it's convex, which ones are the top, which ones are the bottom. And that allows you to sort on these intervals. And so now in logarithmic time you can find out which interval does this point, this x coordinate you're looking for, belong to, which intervals get the top and the bottom. So I think in this instance we're just going to brute force over our triangle, but in theory you could perform an algorithm like this given a convex shape. Supposing that I guess you'd have to like somehow, once you got these points, to figure out what these points are and then figure out where, n log n pre-processing time obviously, right, to do this, because you got to sort these line segments. But you could do that in theory, which is not bad. I'm gonna lay down again, man, just for a few minutes. I don't know, man. I don't know what it is today. That's the problem. You start laying down, you just you're just done. As a programmer, you just don't want to do anything anymore. Taking all these breaks. What do you mean breaks? What is that? What is break? What do you mean? All right. So what was I doing after all? I was thinking. I was thinking that. Huh. Huh. What was I thinking? I was thinking, right, we can write a routine that will scan over the triangle, and part of that routine will say just try all 3 line segments in the triangle to find out which one of them gives you the highest x coordinate and the lowest x coordinate at that point. Oh no, you've got to be careful. No, you got to try all three to figure out which line segments are defined for that point. Yeah, that's what you want. In other words, right. Yeah, that makes sense. Let's do it. We could do our x just vertical. The x coordinates. Which one is defined? Meaning it includes that point, or well, I guess it would be. Yeah, these 3 points you've got. We could sort the points from left to right, and then say, you know. For that particular line, there could be you got to be kind of careful though, because the edge case would be if there's if there's 2 lines of the same x coordinate, that means you're looking at a vertical line. Interesting. Sorry, I'm like freaking dozing off into La La Land over here. I'm still here, but I'm just, my brain is kind of a lot to process today. Also, you know what? Another reason why I kind of want to lay down is my neck aches after a couple of years of staring at the computer all day. You know, because I work and I stare at a computer, and then I come home and I stare at a computer, and 2 years of that definitely do a number on your neck. So yeah, it's kind of, and my bed isn't like super comfortable. It kind of needs a little bit of little extra work to get it just right. It's like not quite right also. And I haven't been exercising the past couple weeks, so I kind of want to take a break. Oh man, shucks. Right, so, what am I trying to do here, after all? What is it? What's the thing? What is the correct, sorry. No, I think I understand what to do. You have a triangle with an orientation and direction, right? And you want to say, is triangle filled? And what we can do is say, we can write a subroutine that says triangle filled with, takes 3 points and figures that out, right? And then our, I guess we can say, you know, like get triangle maybe is better, right? Get the 3 vertices that are associated with that particular row column position with an orientation with a size, right? And then we can say, so we can get triangle verts, we'll call it that, and then we'll say is triangle filled, which takes these vertices. And then the way we can operate is we can sort these vertices on the x coordinate, and then we can say, you know, do another subroutine that says get triangle line or get vertical line, something like that. Get triangle endpoint or get triangle vertical or get vertical line of triangle, something like that, or just vertical vert triangle line, something like that. And that'll give us all the vertices at a particular x coordinate, given that triangle defined by 3 vertices. So what it'll do is check, it'll try to find it'll check your 3 vertices, and you can just do it brute force, because obviously a triangle only has 3 vertices and there's so much stuff to look through. So brute force for which points from left to right, we kind of want to say, now how does this work? It's like, there's 3 line segments to consider, and we want to know which line segments intersect that particular x coordinate. So there should be 2 or just 1. And if it's just 1, obviously, then there's only that line segment is like a side. That's a vertical side. Excuse me, but oh, excuse me. I guess we just want I mean, yeah, I mean, it's easy enough to just take the 3 different pairs of vertices and check sort them on their x coordinate, and then check if the x coordinate you're looking for is between those, for each of those points, if it's between the x coordinates. Yeah, I guess that's simple enough. Yeah, never mind. That's fine. That's fair. And then you can compute the y coordinate given the x coordinate. Huh. Oh. All right. Yeah. All right. Okay. We'll do it that way. You get 3 vertices, and you end up with 3 line segments, and then you perform all your processing on these 3 line segments. Or, excuse me. Yeah, you could also just get 3 line segments instead of 3 points. That's probably better if we're gonna do the processing directly on the line segments. Yeah, and each time you want to convert the each time you want to get the um, y coordinates, just a simple bit of arithmetic you do. You can even go further and pre-process that arithmetic by creating a lambda function type of thing and returning that. I think it's kind of excessive though. Don't really need to do that. Yeah, so, huh. Excuse me. Then you get these two y coordinates, right, and the same x coordinate, and then you can provide those two vertices to the vertical line check thing, which is just going to loop from one, what do they call that, from one vertex to the other. Even better than that, instead of, because we already know it's a vertical line we're operating with, we don't need to give the 2 points, we can just return, like get the points in between, or like return the points in between as a set, as a sequence rather, and then that sequence can then be processed iteratively in another part of the program. You could even go so far as to just check directly and just say, you know, is vert line filled with some, is cross section filled from some x coordinate, and do this all in one shot, where you get the figure out which two line segments this x coordinate intersects with, figure out which two line segments, then use the line segment formula to, use the line segment to get the line formula, then to get the y coordinates, and then I guess return the sequence from that, from one y coordinate to the other y coordinate, the range of x with x values appended, those pairs. Right. I could obviously sort the two y coordinates to do that correctly. Yeah, that's fine, I guess. It works. Yeah, you can even go so far as to, and then you get that collection of coordinates, and then you can just check using that other routine, like is for each map, each of those, every one of those values has that bit set, and then obviously you can write another routine that checks that this is true for every x coordinate as well. Now that's a tricky thing, is which x coordinates do you need? Where do you stop? Where do you end? Very interesting question. Again, you could just take the you could just take the coordinates, the x values of the coordinates, and then sort them, and then that gives you which x values you need to look at, right? The range, exact range. It's sort of a simplified problem, so you can just do it that way. You can do it that way. It's simple. Yeah, there you go. So that gives you your is filled routine, and then you loop over all the different orientations, all the different sizes, possible sizes, right, which is effectively the size of the board, and then loop over all the different possible positions you could be searching for triangles in. And finally, once you've looped over all those things, you've written this code that performs this geometric calculations, or just these sort of pixel calculations, however you want to call it, these calculations, graphics calculations. Once you've gone through all that, then you say, okay, if it's true for these different combinations, if you do have a triangle that's filled, then you're going to get you're going to have this sort of size variable that while you're looping through all this stuff, I guess a reduction we can do. You update the size to the maximum of the new value and what the previous size was or is. And you don't just want the size though, that's the thing to remember. So that's going to always be the size of the isosceles portion, the right angle part. So the area, yeah, that's fine. You can do that to get the size, and then it'll tell you the area from that size. So it would be, because it's always the right angle portion, it means it's going to be height times width divided by 2. So it's just the return value of this function squared divided by 2 is ultimately what you end up with. And, is that true? I'm actually not sure about that one. Because you could have what is that, 1, 2, 3, 4 versus a 1, 2, 3. That's just incorrect. I'm sorry. I take that back. Shucks, man. How do we calculate the area for each of these now? I guess it depends on the size and the orientation. So you really don't want just the size. You actually do want there's a size and orientation function that you got to calculate to get the area as well. Ugh, this problem's got so many pieces to it. I mean, it's a good problem. I appreciate it. But it's definitely like, man, this is a whole lot of programming and a whole lot of thinking for something that's kind of trivial, in some sense trivial. Yeah, I'm wondering, this is the kind of problem I would want to write some kind of machine learning algorithm to sort of figure out what the algorithm is, something like that. Figure out a generalizable approach automatically, rather than trying to program it from scratch. It just seems like really a lot of time. It's definitely one of the problems I want to look at later, I think. There's a whole boatload of different machine learning things I want to explore, want to work on, tinker around with. That'll be great. It's going to be good. It's going to be good. But until then, we're just kind of meandering about here with these problems. Meandering, just lots and lots of meandering. Meander like nobody's meandered before. Meandering. Lots and lots of meandering. There's still something missing here, though. What is it? It's... yes, this size and orientation to area function. Okay. So, depending on the orientation, depending on the size, there are different areas you could have. So in one orientation, I think in every orientation you're looking at the 90-degree angle. Yes, that's true. But the problem is you could actually be looking at, if you're looking at 2 pixels, right? Size of 2. Size of 1 doesn't work. So size of 2. If you're looking at an angle where, oh no, that's very interesting. Right. Yes, that makes a lot of sense now. Okay, I get it. I see the issue. So the length in pixels is the same, but the problem is the area is going to be different. And the issue here is if you're looking at let's call it an orientation, so it could be axis aligned orientation, right? The 90-degree angle is axis aligned, meaning one side of that 90 degree is on the x-axis, the other side is on the y-axis. And then something that's off-axis, where they're on 45-degree axes, right? So the 90 degrees sort of hops between one 45-degree angle and the other 45-degree angle, or the other sort of the negative 45-degree angle is maybe the way to think about it. Those two lines, those two axes, those two lines. The problem is that maybe those have the same number of pixels across those axes, so 2 by 2 and 2 by 2, but because one of them is on a 45-degree angle, it actually has a real length more like the square root of 2 times the size of a pixel, right? Rather than 2 times the size of a pixel, as the other line has. So what you end up with is an area of, when you do your base times height divided by 2, it's not actually just 2 by 2 divided by 2, which is 2, the area, which also is incorrect as well, by the way. You don't actually end up with 2, you end up with 3 pixels, because you actually end up with 1 full pixel and 2 half pixels, and those 2 half pixels get rounded up to 2 full pixels, so you add one pixel. So that's kind of interesting as well. It would technically be however it is that you round up the number of pixels. You would actually end up with excuse me, an area that's more like square root of 2 times the base times the square root of 2 times the height, which is, in fact, 2 times the base times the height divided by 2, which is more like the base times the height, which is 4. It actually is exactly 4, so exactly correct. And in this instance, you do end up with, does that end up being correct? I'm not sure if it is correct. I think the issue has something to do with, you end up with, yeah, I guess it is correct, because in this case you don't have to round up the half pixels. You end up with, maybe it's not correct, I'm not sure. If you did, let's say size 3, number of pixels you would get should be 9. So 1 plus 3 plus 5 does give you 9. Now that's very interesting. That's actually like another proof that that the summation of odd numbers is a quadratic number, right? Every sum of consecutive odd numbers starting from 1 is equivalent to a perfect square. And that, what we just described, this geometric, is a geometric argument for the same thing. Well, that's really cool. That is really cool. Wow. Not sure if it's a geometric argument for it, but it coincides with that. Actually, it might be the other way around. It might be the proof that this idea I have for the number of pixels required for the area is correct. It's because you're adding each time the previous value plus 2 pixels flanking it, which is another odd number. So you have a sequence from 1, 3, 5, 7, etc. This summation, which is always a perfect square, and happens to be the size squared. Right, 1, 2, 3 is 9, is 5 plus 3 plus 1. So next thing we do here is consider, right, so okay, what about the ones that do have the half pixel that becomes a full pixel? The area that you compute, you've got to, I think what you end up doing is you take oh, that's very interesting. So if you took the regular square and you cut it in half, that area, there, right, you're basically taking these half pixels and considering them, some of them to be full pixels, every other one to be full pixel. What you'd want to do is take this size and say, let's say what? You'd want to add half of it, I think. You add size over 2. What about like 3? Right? 3 by 3, you get 9. Half of that is 4. So you have 1, 2, 3, 4, 5, 6. And I wish I could show you what I'm calculating in my head here. 1, 2, 3, 4. I think I got 7. For a 3 by 3, you have 7 pixels. 3 by 3 triangle. 90 degrees, axes aligned. I think I got 7 pixels. Now 3 by 3 divided by 2 would be 4.5. Definitely see the 3, and then there's 1, 2, 3 halves, which gives you 4.5, right? Well, those 3 halves become a whole. So instead of 4.5, you get 3 plus 2 times those 1.5. So how do you figure that? How do you figure that one out, though? It's actually, if you were to round up from 4, no, you don't want to round up from 4. What you want to do is calculate the number, then subtract size over 2, and then add size. I think that's what you want to do, which is equivalent to adding size over 2. So 4.5 plus 1.5 gives you 6. Yeah, that's what you want. So depending on the orientation, you have 2 different possible orientations. One is y-axis aligned, the other is 45-degree angle aligned. One of them you want to take the square of the size, the other one you want to take size squared divided by 2 plus size over 2, which ends up being n plus size of size times quantity, size plus 1, quantity divided by 2, which is another, yeah, so it's either size squared or size squares plus size, quantity divided by 2. Interesting. Very interesting. But yeah, kind of neat. Depending on the orientation. And yeah. So you can write another subroutine that says, you know, you can map the different orientations to the different functions, something like that. Just use a hash map. That says if you're one of these values, or rather, can you use a set as a key to a hash map? I don't think so. Well, yeah, use a hash map. I think the simplest thing. You just the eight different orientations map to 2 different functions. and you could just, I don't know, write like a, name a variable to the particular two different functions, and then just plop them in there in the map. Keep it simple. And so you would apply that map to the size, and then that value is what you'd compare to get the area at the end of it all, to get the largest area. And you're done. That ought to be it. Yeah, that's it. That's a doozy, man. I think what I want to do is just take a break. It's probably end stream here. Just kick back, relax. I realize there's probably more I could do. I kind of want to go get food, come back, and either code some more, or just like, I don't know, dick around on the internet and then go to sleep, because I'm kind of worn out here. Yeah, all right, it's about time now. Timer. There's a lot of freaking pieces to this problem, man. Holy smokes. Or at least the way I'm doing it. Jeez, I had to really think about all that too. Which is fine, but dang, man. Dang. And again, I would reiterate, I would think I would like to write something that's sort of a machine learning algorithm that can piece together all of this given enough data. That would be an interesting experiment to see how we do. How do we do? How would we do? Anyway, there's a lot of different machine learning sort of exercises that I can do that I think would be neat, fun to do, interesting to do. All right, let me go ahead here and let me get going here. So thank you all for watching. Talk to you soon. It's been interesting. It's been fun. Oh no. Let me turn this off now. It's been interesting. It's been fun. I think that'll be it for tonight. Yeah, tomorrow I'll come back, do some evangelizing on Twitch tomorrow, and probably code this up tomorrow. There's a whole bunch of pieces here I want to put together, and then boom, should be good. Get on to the next problem. Man, today was like a crawl in terms of how many problems we got done. This was like, what did we start at 125? We did 125, 126, and just boom, stuck at 127. Perfect. Okay. Well, anyway, let's data juggling. Yeah, this is what I'm talking about, man. Talk about juggling data. This is definitely something I'd want to do with a machine learning algorithm. It'd be so cool if I could figure that one out. Yeah, let me go. Let me get going. Yeah, I'll go to sleep. Tomorrow's a new day. I'll get food. And yeah, let me go. So thanks again. Talk to you soon. Take care.